Hello, ladies and gentlemen. We are back. Back for another day of language programming. When we left off, we just finished our parser. We tried building an AST, an abstract syntax tree, but I had completely forgotten how it works, and we just floundered for a little bit. But that was mostly a demonstration of what not to do, how to build a broken AST. Today we're gonna make a functional one that'll handle a few rules. It'll be really simple. We're just gonna make it do something like, we're just gonna construct an AST out of something like 1 plus 1. We're gonna save that assignment thing like int var equals 1 plus 1. We're gonna save that for later, right? We're just gonna break it down and just do a simple math evaluation language for now. Let me make sure the stream is running and that I can hear it all right. In case it's not working. Do I have audio? I can see myself. Huh. I don't have audio on my end. Strange. Okay. Well, I heard something. If you can't hear me talk, then just say so, but I'll just keep going. Okay. Just the wire fell out of my headset. That's great. Okay. Anyway, let's get right to it. Without further ado, so again, we're looking at Crafting Interpreters. It's an amazing book by Robert Nystrom. We are probably picking up around chapter 6. It's all in Java, but I can show you how to do it in C. But the most important thing is that you see these rules right here. These dictate the language that we're going to do. We're going to cut some corners. We're probably not going to implement all of it for our use case. We just want to make a very simple C-like language. But I think this is probably as simple as you can get. But anyway, any expression, ultimately anything you write in code, at this point where we're doing 1 plus 1, that'll just be equated to an expression. And then you go further down the tree, an expression can be an equality operation where you're checking, where you're doing like an equality comparison. And then you have a comparison where it could be like less than or equal to. And then it could be like plus or minus, multiply or divide. It could be an inverting operation, a unary operation. And ultimately, as you go deeper and deeper down the tree, you're going to hit a primary, which is, it's either a number or a string or true or false. It's going to be an absolute value that you can then bring back up that tree of rules to collapse every additional layer. So you have 1 plus 1. It can be evaluated as equality. You don't see either of these, so you go to comparison. You don't see either of these comparisons, so you go to factor. You see plus, and then that means, sorry, you see the number 1, but it's not a plus or a minus, so you go to unary. It's not a slash or a times. It's not a bang or a minus. And then you get down to primary, and you see that the token that you're evaluating is a number. It's 1. And so you know that this expression right here is a primary expression. So you push that back up, unary, factor, term, and then you see the next token is a plus. And then you're picking another factor. You go back down. You have the 1 plus, and then you go back down the tree, and you see it's a 1. You bring that back up, and then you have 1 plus 1 as that expression. It'll make more sense as we go through it, but what we're doing right now is recursive descent. And you can see he has a little comparison right here where it's all about precedence. So when you were in school and you learned about PEMDAS, parentheses, exponent, multiplication, division, addition, subtraction, those are the order or the precedence in which you want to group different operations. And the same thing happens in languages, which is what we're demonstrating here. These are lower precedence, and then primary is the highest precedence. So I guess let's just get started on it. Oh my God, 2 people watching right now. That's crazy. Okay. So let me just copy that over and we'll get started on it. I was already writing a few of these when we were trying to make the broken construct AST thing. Let me delete that real quick. Get this wire out of the way, it's bothering me. Okay, primary operation, let's just delete all this stuff. Make value expression. Yeah, let's just delete all this. We don't need it anymore. That was just experimental. And we're gonna drop this in. This is our guiding light. These are the rules that we're gonna implement. And so, let's just get started. The first thing that we're gonna wanna do is we're just going to do expression E equals expression. And this will start us in the recursive descent process. Again, we're not doing statements or anything higher level yet. We can keep adding to this, but we just want to make sure the internals are functional. So we're just going to work on turning one expression into an abstract syntax tree. And you will see how we do that. We already have that hash table. We don't need it quite yet. So I'll just write this out again. We have expressions that break down into equalities, that break down into comparisons, that break down into terms, which are plus or minus. Remember, we're going from lower precedence to higher precedence. So terms are plus or minus. Factors are multiplication, division. Unary is where you have an inversion, or like, you know, that exclamation point or that minus where you're setting a number to negative. And then you have primary, which is a single value. Primart. So all of these are going to need to return expressions like this. Let's just set it to null for now and return it and make sure that it compiles. Great. Okay. So I can just turn all of these into little functions we call. Gonna do that, press end on my keyboard, parentheses, curly braces, return null. This would be silly if I could quality comparison. Nice. Expression E, expression to a pointer. Yeah. Comparison goes to terms. Terms go to factors. Factors go to unary. Unary goes to primary. And primary ultimately returns something. So we can do if tokens, next token, dot type equals token number. We're only going to evaluate numbers for now. We're going to make a new expression. Did we make an array yet? Okay, so we have this expressions array, right? And we have expression count. This is an arena that we're just going to take elements from and return them up the stack or up that recursive function stack as an expression that we build. So we can do expressions plus expression count, because we just want to return a pointer to a slot in that array that is currently unused. And let's make it null. Expression pointer E equals null. And if the next token is a number token, then we set E equal to that. Remember, if you do something like this, then you'll return the actual object in memory, or you'll copy it over from that array. We just want a pointer to that slot in that array, so we're doing this. This is just pointer arithmetic in C. And so we can do E type equals expression primary, E data primary AST equals tokens, next token, and then we'll increment it from there, and then we'll return E. And so, of course, I haven't added any of these things yet. It's all broken. Primary, oh yeah, and I have them in reverse order. We want to, because we're going deeper and deeper, we want to put unary above factor, which is above, oh God. Unary above factor, which is above terms, which is above equality, which is above comparison. Getting it all backwards. Unary goes to primary, factors goes to unary, terms go to factors, comparison goes to terms. Yes, okay. It's all ordered now. And then up here we'll make expression go to equality. Next token is undeclared. Okay, so this is going to be a global. I'm just going to put it up here. And this is how we're going to process the tokens. We're going to start with next token is 0. We're just going to set it down here right before we break down the expression. Okay. Unnamed tag. That is because I made an expression type primary, which we haven't yet added. And there's a bunch of other stuff I haven't explained. I left some notes. I noticed a bug. I explained like the modulo operation we did a bit better that I kind of glossed over yesterday. So if you have any questions, just ask and I'll slow it down for you. Expression none. We want to turn value to primary. And then we'll just do it all again. Unary, factor, term, comparison, equality, binary. I don't know if we need half of those, because ultimately all of these expressions break down into binaries or primaries. And I guess that's reasonable. You can do primary expression instead of value expression. I don't know what I was thinking. What the hell happened? I did Control V, there we go. And then for binary, have a binary expression, and that's like 1 plus 1. So you're going to have a pointer to the left expression, a pointer to the right expression. You know, like on the left, you have 1, that's the left expression. On the right, you have 1, that's the right expression. In the middle, you're going to have a token, and that will just be the operator. It could be like plus, minus, it could be anything. Don't need that, don't need any of that. Okay, and then we're going to substitute or replace primary expression. Let's call it primary. That binary, we can start with those. We're also going to need a grouping for parentheses. And inside that, you're just going to have another expression. Grouping expression. Group. Make sure that compiles. Cool. Okay, and then we need a type for grouping. Expression grouping. Okay. And we forward declare it up here so that we can contain pointers to it down below. Just so we can have like some kind of nested structure that can refer to itself. You want to forward declare when you get to that. So we have all these functions. Expression can be equality. We need to replace all these with E, return E, return E, return E. Okay. So all we're going to test right now is that 1 plus 1 idea. We're going to go down this tree until we get to terms. So we have the number. We have primaries returning the number. That's good. And then we get to terms. which are plus or minus, and then we'll do while tokens, next token, dot type equals token plus or token minus. This will be a binary expression. And so we'll do, we're going to swap around the pointers to the expression that we just got back from factors, which returned from unary, which returned from primary, which returns this number. So at this point, E, expression E, is going to represent one of the numbers, a primary value that contains the number 1. But we don't want to overwrite it, and so we're just going to do like a expression, last expression equals E, laced. Why not? And then we'll set E to a new expression, expressions plus expression count. This will allocate a new expression, and we'll access it. We'll set the type to binary. E.type equals expression binary. That's how we define the enumerator. E.data.binary, going to access it as a binary. Dot left equals that last E, that number 1. So we get 1, an expression, a primary expression representing the number 1. We get that back here. We set it to this pointer, last expression, and then we assign it to the left. Dot operator. That's going to be the token, and so we'll do tokens, next token, assign that token, edata.binary.write equals factors. And then this will search for the next token, which is the number 1, and return it up. And I think that should be everything. I could be wrong. But we get the 1 from the factor right here. We fill out the binary expression, and we return it up. We're going to ignore comparison equality expression all right here. We got the number 1 returning. And you see that represents that, I think that was term. You can see that represents the language that Nystrom defined here. So you have the factor, we get that factor, we check if it's a plus or minus token, and if it is, then we get another factor token from it. And you can do this indefinitely. That's why you have this little star here, because it can keep repeating itself, which is why we stick it into a while loop. And the same process repeats for pretty much every term. You can see that they all share this in common. So you call the next function down in the precedence, you check for a few tokens. If you do get a token like that, then you put it into a while loop and you check what the right token is further down in the tree. The unary is different, we can get to that later. It's either a unary or primary. Yeah, okay. So we're compiling, that's cool. I guess we'll just test it out. And I left a bug in the parser and I didn't realize this. So we'll do 1 plus 1, and you'll see that when we debug print out the tokens, we only have 2 tokens. They're both numbers. Why is that? Let's step into the broken parser that I left you with yesterday. Set a breakpoint there. I'll do 1 plus 1. And then you see that we read the number, and then we progress to the next character, right? So the next character is now the plus symbol. And then down here we do plus I again. So we skip past that plus symbol, and then we have another 1 as that character, which we then interpret. So this is broken, and the way that you can fix this is just to get rid of this plus 1 at the end. And then we can start getting even more sloppy. I'll show you how to compress this later. But for any given rule, we'll just advance to the next token instead. Else if is white space. Just do I++ here. We'll do, I think that's good. We don't need to do I++ for right there. I could be wrong. Let's see what happens now. See how many tokens we get if we do 1 plus 1. Okay. So now you see we have a number token, a plus token, and a number token. So that solved it. And then we're going to step into expression and see what happens, because we print the tokens, we do the debug print right there. And then we're going to start stepping through the recursive descent functions to create the abstract syntax tree. So we have 3 tokens. Okay, well 4 if you want to include the end of file token. But we have a number token, a plus token, and a number token. So we step into expression, which steps into equality, comparison terms, factors, unary, primary. We're going to check what kind of token that is, and we see that it's a number token. So we allocate a new expression, set that expression to primary, and then we assign that token, that number token, to that primary expression. So now if we look in T, we'll see that its type is primary. We can check out the union of the data. Remember, the union, it all occupies the same memory, and depending on what you want to access, it's like a tagged union or discriminated union. You need to assign some kind of type to this data structure to determine which field to access. And so it's a primary expression, so we're going to check out what that contains. T is for the token. It's a number token, and then inside you see that its integer is 1, which means that this number token contains the value of 1. So we have the right data in there. We're going to pass it back up through the recursive descent structure, and then we're going to check for the next token, which is, in this case, we're at token 1. Let's look in the tokens right here, and you'll see that it's a plus token. So then we assign to the left, we allocated a new expression when we did this expressions thing right here is our arena, our global arena, plus the expression count, just like advancing us to allocate a new slot in that arena and giving it back to us. Assigning it to binary, and we're assigning that 1 expression to the left pointer in the binary expression. Remember, we can go up to it, binary expression. It contains a pointer to a left expression, and a pointer to a right expression, and an operator. And so we can step through this and see that it's a binary expression. We'll go to the binary data, and we'll see that its left expression is a primary. Let's go to that, and we'll see that it's 1. So this is correct. And then we will assign that plus operator, and it tells us that it's a plus token, and then we'll go back down that tree for that right operator. So we'll go back into unary, primary, and we'll see that the next token is also a number, and we're going to assign a new expression for that, return it back up, and then you see that we assign it to the right token. And so then we check the top of the while loop again to see what the next token is. Our token count is at 3. Let's see what that is. That is end of file, so it doesn't match plus or minus. So we return, 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 go all the way back up, and then we have that token, which of course it's a binary. We'll check it out. On the left, we have a primary. On the right, we have a primary. The operator is a plus token. Let's go to the data for these. 1 and 1. There you see, people. That is how you do recursive descent for a language. You need to keep in mind the precedence. You can design any precedence you want, more or less, as long as you get the order of operations correct. Like, you can do it any way you want. There's a bunch of other ways to do it, but they're sloppier, and this tends to be the easier one to understand. So there you go. But all we have right now is just, all we filled out is term for 1 plus 1 and primary, that number thing in primary. That's all we have so far. And so that's what we call at the bottom. So now we're going to, what we returned is an abstract syntax tree. This is the title of the stream, an AST. It tells you how the language, as you step through the language, how you evaluate it, how it sorts itself. And so we can also print that out to make it easier for us to see. And so we can just do print AST. And we'll feed it in an expression. Or print expression. Yeah, print expression. How about that? And so now I need a new function for this. So we'll go back up to expression, and we'll just do the same thing. We'll do void expression pointer E, and then E can have a type, so we can switch based on that type. We'll have case. All we have right now is a binary expression, so we'll just do that. Binary and primary. Yeah, because inside the binary expression, it contains primary expressions for the ones. So we got to do that. So we'll have two cases right now. We'll have case expression primary and expression binary. And we'll put routines to print either thing in here. And let me just add a little string counter so we can drop that stuff in here. We can just call it AST string, or yeah, why not? AST string. We'll have 2048 characters. Then we'll have int AST string count. And we're going to use sprintf to store all the text for this tree and then print it out at the end. So let's do that real quick, right at the bottom. We'll do printf, little thing like that. We'll do AST string. That's it. Cool. We're compiling all right. And so now let's do void print primary. Give it an expression. We'll do the same for binary. It's not really printing, it's more like storing the string, but whatever, it's just semantics. Primary, print primary right there. Print binary. Need to give it the E expression, or yes. Okay. And so now we're going to use sprintf. It's a function where you give it a text buffer, whatever text you want to store in there, and then the format of that text. And it also returns an integer. If you see, it also returns a little int. That is the offset into the buffer. The buffer that you put in, it'll give you the offset of the text that you've written into it. And so this is where we use AST string count plus equals. Then we'll do AST string plus, remember this is pointer arithmetic. We have this buffer. We're going to give as printf the location in the buffer we want to write to. And then we'll do, we want to, well here, let's do this in primary. Because primary will have another switch statement here. We'll have E type. And we'll have case. All we care about is primary expressions right now. So we'll do expression primary, and we'll store it in there. And then we'll have like a default case. And so for the number primary expression, we're just going to append the number right there. And that will be E data primary T dot data dot integer. We're storing a token in the expression, and the token has its own data field, its own union, which can store an integer. So that is what that is doing. And so then in print binary, we can have two expressions in here. And so we'll call print expression on E data binary left. We'll add whatever symbol the token operator is. And I guess, do we have print tokens or token string, or I guess I should make a function like that. You can do void print token. Do I have something like that? Yeah, okay, print tokens, but not print token. Okay, so we'll just make a print token array, print token function that takes in a token T, and we'll do a little switch statement on it, switch T.type, and we will only take into account the plus or minus operators for now. So we'll do case token plus, right? And inside it, we'll just do the same thing. Do this. But instead of giving it some kind of data, we'll just do a little plus symbol right there. Isn't that nice? We'll add a default case. I guess we could add a -1 in case we want to do minus. And we'll change that symbol to a minus. Okay. So we'll do print expression, print token, data binary dot operator, the operator token, and then we'll print out another expression for the right expression. But because we're calling print expression below us, we need to forward declare it. Just do that at the top. Print expression, void, yeah, okay. That all compiles. Let's just see what happens. We're feeding in, we're calling print primary, print binary. So remember, we feed in a binary expression. This calls print binary. Inside print binary, we know that we have a left and right expression, so we call that. But those left and right expressions are primaries, which we then print out right up here, and we're only handling it if it's a number. Yeah, print primary. I should probably switch based on what type the token inside of it is. Let's do that. E data primary, T data type. We'll do case token number. Data. Right? Yeah. Okay. So let's just see if this works. Let's go page down all the way down here. And we'll just see what happens. Let's see what we print out. Do 1 + 1. And then you see at the very bottom, this is us printing out the abstract syntax tree of 1 + 1. There you go, ladies and gentlemen. Let's see what happens. Well, let's see what happens when we do 1 + 1 + 1 + 2. There you go. There you have it. We're printing out the abstract syntax tree for 1 + 1 + 1 + 2 with this little recursive descent printing function. That's how you do recursive descent to generate an abstract syntax tree. So whatever do we do now? I guess we can add parentheses, like what happens when we do, let's like wrap this in parentheses to give it precedence above the other ones. And then you see that I guess we got to print expression, but we never stored, we just returned null. Yeah, okay, so we pass it through, we pass that, I'll just show you what happens and what we need to do. We crashed when we hit that parentheses, and we'll do it again. We'll go into expression. Oops, I stepped past it. Need to press F11. Okay, step into that, go to quality comparison terms, factors, unary, primary. E we set to null. The next token, we're at token 0. The token is a left parentheses, but we don't have a case to handle that. So we just step back and return null. And then when we get to print expression, we crash, right? So now we need to handle closing parentheses. And we'll do that with, just do else if tokens dot next token dot type equals token left parentheses. Then we'll do all the same stuff. We'll allocate an expression. The expression type will be a grouping because we want to group together these variables. Primary T E dot data dot grouping equals expression. And we'll just recursively call expression again. But of course we need to forward declare it. So we'll do expression like that. And something's still wrong. Else if tokens dot next token. Oops. Okay. Still got errors. Data.grouping.e. There we go. The expression inside. And why is this wrong? Oh, dot. I'll just set it to grouping. I call it group. Okay. And so we also need to advance the token, next token, token plus plus, to move past that left parentheses. We need to do that before we call grouping. And then once we have that, we need to check if tokens next token equals dot type equals token right parentheses. We need to close it. You don't really, apparently parentheses. Are you on a treadmill? Software dinner ad. Yes, software dinner ad. I'm on a treadmill going a leisurely 2 point something miles per hour. So parentheses, like all you really need is an opening parentheses. The right closing parentheses are rather useless when it comes to programming languages, but it's nice to keep it all tidy. And so we'll just do else. If you don't have one, we'll call it a processing error, and we can printf expected a closing parentheses following the grouping. I don't know. Okay. And we'll do next token plus plus. Otherwise, we have an error. Yeah, okay. So let's see if that fixes our stuff. Oh, but we also need to, we can run it. And you'll see that we can print everything, but there was no case to print a grouping expression in the print expression, so we need to add that next. So we'll do print expression, case, expression grouping, break. Do you work as a SWE software engineer as well? Yeah, I guess. I'm self-employed. I'm working on my own game engine, or multiple little projects. But yeah, I do. Like, I just do this all day. This is what I do with my life. Print grouping. And so to print a grouping, let's do the same thing right here, but we're just going to have one. Going to do grouping.e, and then inside of that, just steal these and we'll just wrap it in parentheses. Open parentheses, close parentheses. There you go. We want to call it print grouping, not print binary. Print grouping. Okay. That should work. So now we will do that 1 plus 1. And there you see it. There, right down here, we're printing out the abstract syntax tree of a grouping of 1 plus 1. Let's do that again. Plus 1 plus 2 plus 2. Why not? Let's get freaky. Can we handle minuses? Yeah, okay. So we typed in parentheses 1 plus 1 plus 1 plus 2 minus 2. And so we're printing out that whole abstract syntax tree at the bottom right there. So, I mean, if you want to keep the language simple and you just want to evaluate math, then this is how you do it. But of course, we're only printing the abstract syntax tree. We're not interpreting or evaluating these expressions at all. We're just printing out the form they're taking. And so the next step would be to write code to evaluate this. And so, like, to run this code. So we have this code, we broke it up into tokens, and then we interpret it in an abstract syntax tree, and now we can actually start running it in real time if we write more code to do that. And so, of course, we can only handle plus or minus right now, but we can still evaluate it. So we just write evaluate, a little function to evaluate this expression, right? And so we'll go back up here, and then we'll do, we want to work with objects. So we have tokens, we have expressions, but now we want to start manipulating actual data. So now we need to make another struct, type def struct object. And of course we can also do type def enum object type. Call it object num. Well, first we'll do none. num. I don't know why I did that. String. Bool. Char. I don't know. There's a bunch of different objects you can take. Like in here, you would even do function. Once we get to functions, conditional. I don't know. I haven't gotten that far yet. Let's just figure out what we got to do. So we got to do object type, and then we'll have a union. We'll just call it data, like I usually do. You can call it anything. You can like evaluate it as. I just do data whenever I do a union. That's just how I remember what it is exactly. And then inside, depending on what the object type is, if it's a number, then you'll access it as integer. Why not? See if that compiles. Of course it doesn't. Why would it work? Unresolved external symbol. Oh, that's because we never made the evaluate function. So now we want to assign evaluate to an object. Object O equals evaluate, and it'll be a pointer. Because we're going to assign it from another arena that we're creating up here. We'll just call it object objects. 2048 of them. Why not? And int object count. We'll start that at 0. Then we'll do the same thing down here. We'll do object count equals 0. Just refresh it before we call the evaluation function. And we have a parsing error. We have a processing error. Let's do, where are our errors kept? Parse error. Processing error. We'll just call it runtime error. Runtime error equals 0. And so we'll go back down to the bottom. Set our little runtime error. 0. Let's do the same for processing error. If we want to run this in a loop, like a REPL, what does REPL even stand for? R, evaluate, prompt. Man, I can't remember. REPL meaning, let's Google it. Read, eval, print loop. Read, evaluate, print loop. So we could wrap this main function into a while loop. And then you type in stuff, we evaluate it, we print it out, and we just do that over and over. That's a REPL. Read, eval, print loop. We don't really have that yet. We don't really care. We're just going to keep it as is, where you just run it once, and then it ends. Parse error equals 0. Okay. And we still don't have an evaluate function. And of course, we have more errors up here where we have this thing for objects, but where the hell is an object? Where is it defined? We haven't defined it yet. So let's move all this above. Let's put on object evaluate right here, and it'll take an expression. And we'll just return null for now. There you go. And we'll put it all up at the top of the file with our other stuff. And now we can start building successfully. So how do we want to do this? So we're evaluating an expression. We probably want to switch based on what that expression is. So we'll do switch type. We'll do case. We're only evaluating, well, I guess we got to evaluate everything. We're evaluating groupings, binary, and primary. So we'll do expression grouping. Got to get the colon in there. Oops. Got a break. You don't need to add the break after. This is how I set it up. So I'm grouping, binary, primary, and what are we going to do? Now we need more functions for return an object, evaluate. Let's call it evaluate expression, evaluate grouping. Call this above because we're probably going to need to call it again inside these other functions. Evaluate grouping, evaluate binary, evaluate primary. We'll call all these, I guess, Yeah, copy those. We'll do object O equals null, and then inside O equals one of these. Send it over, and then we will return O. And now, how do we fill out all these expressions? Evaluate grouping. Well, we're just going to evaluate expression. This is easy. We'll just do e data grouping dot e. We're sending it in the expression within that grouping. It's just we're going to want to return it. Return. Let's just see if this compiles. Return null. You can also use 0 for a pointer. 0 and null are the same thing when you're working with pointers. It's not compiling. Why is it not compiling? Initializing object. Object O equals evaluate expression. Okay, there we go. So evaluate grouping is taken care of. Evaluate binary. How are we gonna do this? Last time I did something like this, it was like March. Based on the book, Crafting Interpreters, but it's been a while. So you can have a left and a right, so I guess we'll do O equals object, O equals evaluate expression, E data binary left. Will this at least run, and then we can return O. No, it's not working. O equals data binary left. Unresolved externals. Initializing object. You are initializing an object that differs in levels of indirection from int. E data binary left. Evaluate expression. What the hell? Let me just set it to null. Okay, so that works. We're sending in an expression, so am I doing something? I'm doing something wrong, but I just don't know what it is. E data binary, let's just step into it. Binary expression, we have a left and a right and operator. We access it with data.binary.left. E data binary left, evaluate expression. We're passing in a pointer to an expression. What if we just return it? I don't know, I have no idea what's going on. Can I pass in null? Evaluate. Oops. Wait, no. Evaluate expression. Evaluate. Yeah, okay, I just misspelled it. Damn. That's embarrassing. Evaluate. Okay. So we're evaluating the left and the right. And just call it 01, 02. And then in here, we're going to branch based on what kind of operation the token is. So we can do switch E data binary operator dot type. Then we'll do case token plus minus and then yeah, we'll want to pass in. Okay. I guess we can make a function for each one of these just so it doesn't become a behemoth. And we'll do it right up here, or is that what we want to do? I guess that's what we want to do. We can do, we'll return an object, and it will be evaluate term. Yeah, and so we'll have token T, we'll have object O1, object O2. Just evaluate term. We can make these fall through. Evaluate term. We'll pass in the token O1 and O2. Object O equals null, and set O equal to the result. Okay, and so now we're going to have another switch statement based on t.type it's token plus. We're just repeating the code down here. I don't know, we'll figure it out later. It doesn't really matter. Okay, and then we'll switch based on whatever, either of these. Yeah. I guess we could allocate another object, I don't really see. We can just keep pushing more and more objects onto the stack, and if we have a problem, then we can figure out how to compress it later, but we'll just be sloppy here. We just want to build up to a basic working implementation, and then we'll worry about the details once we see that it somehow starts to work. We don't care about anything else. Object O equals null. If it's a minus, this is where we start adding the objects together. So I guess you just do if O1.type equals object number. If they're both numbers, then we'll call add objects O1, O2. Else we'll just give a runtime error. Printf. I need to wrap this in parentheses. Printf expected two numbers in term. I don't know. We'll figure it out later once we actually have errors. Okay, add objects. We'll do O equals. Just create a new object there. Wrap this in. I guess we could do this. O1, they're pointers. O1 type and O2 type. Okay. What's the problem? Equals. We need to do equals equals. Right? Okay. Add objects. That just doesn't exist yet. So we'll do object add objects. And we'll have object O1, object O2. And now this is where we'll add the objects together. So we can do object O equals objects. Remember that pointer arithmetic object count. We'll allocate a new object. And we'll do O equals O1 data dot integer plus O2 data integer. Return O. Make sure that works. Got a warning. Object pointer differs in level of indirection. Okay, that's because we need to set it to O type equals object number, and then we'll do O data dot integer equals that. Okay, cool. So we add the objects together. We'll do the same for this, I guess. I don't know, we can clean it up, the messier we get. We do subtract objects, or let's just make it verbose. Subtract objects. Do plus, minus. Just copy all this, and we'll do subtract. And we will subtract them, like that. So that's all compiling. Evaluate expression, evaluate term, get O back from that, evaluate expression. These are going to be primaries. Left and right are primaries here. Evaluate primary. Okay, so this is where we'll do allocate more objects. Object O, objects plus object count plus plus. O type equals, well, now we need to switch. Yeah, let's not be hasty. Just set it to null, and then we'll do switch based on the type of the expression, and we'll only handle, we'll do like default case. I keep forgetting to do that. We should add that everywhere in case we want to compile this to WASM. We'll do case token e.type. We'll do case expression. No, we want to evaluate the type of token inside the primary expression. So got data.primary .t.type. And now we'll do token number. Are we going through this right? I think so. If it's a number token, then we'll allocate an object. We'll do O type equals object number. Set O data.integer equal to t data integer. And then we will turn that object. Objects. Okay, so now assuming that all works, let's just print out printf. I don't know, whatever all that stuff is that we typed in. We're just going to assume it's a mathematical expression, and then we'll just print out the result. We'll do o.data.integer. Okay, so let's type in. Hey, look at that. Okay. So we got something, we did something wrong. That's great. 1 plus 1 plus 1. This should be 3. This should evaluate to 3. So let's see what we did wrong. Did we not? We probably skipped a lot of steps. Okay. So E is a binary expression. How is that a binary expression? I guess, yeah, let's see what they contain. So we'll go to the binary field. Left is a binary expression, and then the right is a grouping. Okay? What is the binary expression here? Oh my god. It gets verbose. Left is a primary, right is a primary, left is a grouping. Okay, yes. So this should be the 1 plus 1. And then on the right, the grouping, we gotta go all the way back up. Let's check out the right field in this. It's a binary. We'll go to the right field, which is a grouping. Check out the data, the grouping data, the expression. It's a binary expression. Let's go to the binary field. Let's see the right operator. And the data is 2. Yes. Yes. Okay, so the left is the parentheses 1 plus 1 plus 1. The right is the 2 minus 2. Okay. Okay, so let's just step into this and see what happens. Evaluate grouping, binary, primary. I think we filled all those out. We have a binary expression. Let's evaluate the binary expression. It's another binary expression. And that binary expression is a grouping. Evaluate expression, which is a binary, which is a primary, which is a token. It's a number. Okay, it's an integer of 1. Cool. We return that from the primary. O2 is an integer. Good. 1 plus 1. Okay. Interesting. T.type is a plus. We somehow skip this. Let's set a breakpoint for that. Okay. Token T is a plus. T.type. Oh. Just forgot case. Okay. Easy mistake. Default. Please break. Let's add defaults to everywhere else. I don't even know if it's not really necessary, but some compilers prefer defaults. And so we will oblige them. Default, default, default. Okay. Okay. See what happens. Okay. Cool. We got a bit further. But the object types, O1 and O2, are undefined. O2 is defined, O1 is undefined. Okay. I should add print statements to this. This would make everything easier. Yeah, why not? Let's do evaluate term, printf, adding, yeah, do O1, data integer, O2, data integer, do subtracting, just so it's not so opaque to us. Yo, I love these coding streams. Matthew B. Yo, what's up? I love these coding streams that give me motivation when working on my projects. It looks like you're walking while coding. Yeah, I'm on a little treadmill. It's a good exercise at least. You know, it's better than sitting hunched over all day looking at the laptop. You gotta stay in motion or else you'll die. So that's what I'm doing. Yeah, we're working on yesterday. The stream yesterday was us making a parser, which you can see right here. This is us tokenizing all the text. We had a bug in it, which we fixed earlier today, and now we're trying to evaluate all of that. And so we broke it into an abstract syntax tree where we only evaluate like 1 plus 1 or 1 minus 1, for example. And now we're trying to execute that abstract syntax tree. And we have a little bug, and I'm adding a few print statements to fix it. Evaluate. Yeah, let's just make this as verbose as possible. Whatever. Do printf. Evaluating grouping. Evaluating binary. Evaluating primary. Do pdebug. Is that how we defined it? We set a little thing up there just so that we can disable these for later. Let's not. We want to be verbose with the errors for now. You want to see the errors. Are you using VS Code? Vim binding. I'm just using VS Code. I don't think I'm using any bindings for it. It's just raw standard VS Code. That's pretty cool. I've been working on an expense tracker and just got async to run on the rest of my program. Oh, like JavaScript? I fucking suck at JavaScript, dude. I can't wrap my head around async. I mean, I was writing like a website where you need to do async to add in like a WASM file, and so I mean, I got it compiling, but I have no idea how async works. Need to work more on that, but more power to you. Expense trackers are cool. That's a good idea. Okay, yeah, let's just run it again and see what happens. Evaluate expression. Step into this. We'll just do 1 plus 1. That'll be the easiest for us to understand. We won't have a grouping, won't have anything like that. Like, will it actually run? Okay, so we're getting an error already. Cool. 1 plus 1. We step into it. This is a binary expression. We evaluate expressions. It's a primary expression. It is hopefully an integer. We evaluate the other expression. That's another primary. O1 is an integer of 1. O2 is an integer of 1. We're going to evaluate a term. We're going to do plus, adding 1 plus 1. Okay. And then the integer is 2. Okay, perfect. So we return O. Set that. Just, man, it's biting me in the ass when I set everything to null. Yeah, we'll just return null. Don't worry. It's just a placeholder to get it to compile. And then, of course, I forget to set it at the end. Okay, so now I think that's what was biting us. Let me just remove all these breakpoints. We'll do 1 plus 1. Please. 2. Look at that. Look at that, folks. Nah, Python. I'm writing a personalized program that sits on your computer like back in the 90s. That's cool. Yeah, that's really cool. Like, what are you doing to visualize all the data? Like, I mean, of course, you're not writing your own, like, renderer for it. You're, like, creating a window for it or something. I don't know how to do that in Python. I'm most familiar with C, C++, so. But Python is cool. It's pretty easy to use. So let's build it again, and we'll do that 1 plus 1. Hey, 3, look at that. Isn't that amazing? We can now evaluate basic math with this parser and, I don't know, evaluation loop that we wrote. So remember, we have all these tokens. We break it down into tokens. We create an abstract syntax tree based on all the precedences that you see right here. Again, we only have plus or minus working. And then we feed all that into an evaluation loop where we have these objects and we return an object. So I guess we could make it a bit more robust. We can do print object. We'll feed it an O for object that we get back. And now we'll make a function for this. We're just going to carve out the basic steps for everything. So we're going to do void print object, give an object pointer, and then we can switch based on the type of that object. Then we can do case object num, break, just do print object number object D. And we're only handling integers for now. If we want to do floats, I guess, yeah, so other languages like Python and JavaScript, everything is internally represented with a double. You know, like not just a float, a double, which is like 64 bits. We're just doing integers for now. And so we will do object o.data integer. Oh God, default. Breca. Okay. The same thing. Object, number object 3. Okay, cool. Subtracting 2 plus 2. Let's fix that in the debug real quick. Subtracting 2 minus 2. Okay. We can just set that to the resulting integer. Why not? Do the same thing right here. Okay. Just clean up the printf a little bit. Yeah, cool. Subtracting 2 minus 2 is 0. Adding 3 plus 0 equals 3. Number object 3. Main modules used are async.io, tkinter, SQLite, and several others like logging for all the extra BS. That's cool. Yeah, that's I've never worked with the Python libraries as extensively as that, but more power to you if you can get it all to work. That's impressive. We're just doing it in raw C because that's all I understand. I mean, I've worked with Python before, but I don't know. I like I'm so used to writing in C that I don't like the syntax of Python, so I just rather write in C. But that definitely comes with drawbacks, like not being as fast if you just use Python. So yeah, it's cool. So we at almost 700 lines of code, and we can evaluate basic plus or minus expressions. Let's just do like 2 minus 2 minus 2. That is -2. We don't have unary, so if we do -2, then that'll give us a null expression because what even happens there? Let's evaluate that. Let's I guess now we can start fleshing this out more, like adding more expression types that we want to handle. So we're doing -2 now. And so when we try to print it, we're getting an error. So that means that we're not evaluating it correctly or getting the correct expression for it. -2. Step into this, equality, comparison terms, factors, unary, primary. Yes, and so because we don't have a number token or a parentheses token, we just return null. And of course we don't handle anything like that in unary. And so now for unary, what we'll want to do first is we will want to, if tokens, token count equals, do bang or minus. Those are the unary operators. I guess we'll have an else. Expression equals null. Oops. We will do, yeah. We will create a new expression. We do like, yeah. We will create a new expression plus expression count. And then we'll do e dot type. We'll create a new unary expression. So we'll do expression unary. We'll do e operator. What do we have in the unary expression? Have we even defined something like that yet? I don't think we have. Primary expression, binary. Okay, so we need to define a unary operation, a unary expression, and this will contain a write expression and an operator expression. Okay. And so we'll do equals tokens, token count, plus plus. That'll set it to whatever, like the minus or the bang operator. And then we'll set e write equals primary. Oh, and we got to do e data, unary, stuff like that. Okay. Okay. What's wrong now? Need to do type. I keep forgetting that. You can make this way cleaner on your own. I'm uploading this to GitHub. The link is in the description. You can do whatever you want with it. Just, I mean, we're just basing it off of crafting interpreters, so you can make whatever crazy language you want. The eventual plan for this is a minimal C-like language that I can break down into some kind of text bytecode that I can feed into another language that I also have uploaded to GitHub. It's called like VM test, but the eventual plan is to link this, like a higher level language, to my lower level assembly virtual machine. And so we're going to be learning all about higher level language construction design. So right now we're making recursive descent. I have Pratt parsing planned. There's a bunch of different things you can do, but I'll just have those two, and then I'll eventually try and break it down. We'll need to learn register allocation, because I have like registers. I have 32 registers in the virtual machine, and you need to figure out what register you can use without pushing out important data of in whatever operation you're doing. So there's a lot more stuff involved that we're going to need to do, but we're getting there. I've lost track of exactly what the hell I'm doing. Evaluate expression. Unary. Binary expression redefinition. Oh. Yeah, okay. Oops. Okay. Unary. E data. We never added a unary field. Primary. Unary. Okay. So if we have a token like that, then we'll return a unary expression. Otherwise, we'll just return a primary expression. So we'll see what this does. Let's see. Oh yeah, okay. So E is still null. That's because... Why exactly? I know I'm forgetting a step, but I can't remember what it is because there's so many pieces involved. Quality comparison terms, factors, unary. Okay, token. Token count is 3 minus num. Man, that's embarrassing. We want to have a token minus or a token bang. Did I ever add a bang token? Okay, I never added a bang token. We're gonna need to really boost up the token count, so I'm just gonna add some space here. Because in one shot, I'm gonna need to add these to other printing expressions, so we're gonna have token bang, gonna have token plus plus, I'll just call it P plus, gonna have token minus minus, gonna have token equals equals, token not equals, token greater than, token GR, token less, token greater than or equal, token less than or equal. We have bang, not equals, plus plus, minus minus, equals equals, not equals, greater less than, greater than, equals than. I think that is, and let's just add colon, token colon in case I want to add that in. Is that everything? That's everything that I can think of right now. So we'll just start pasting these everywhere in all those functions that we have to print out token names. Yeah. I guess we'll add token and a file here as well. Oh god, what did I do? Case. Break. Let's straighten all this out. Token end of file. What did that do? We will return constant string. Yes. God, please. Okay. Okay, that's compiling successfully. Let's just find that other function where we need to print out all the tokens right here. Already have that. Already have end of file token there. Case. Let's just do the same thing again. Break. Printf. Get those. 3D backslash n I. Okay. Just straighten it out again. Oh god. Okay. But all of that was just a distraction as we try to work out the unary thing. Primary unary right here. Okay. can either be token minus or token bang. I'm gonna set that token. Just see what happens. Okay, so we never hit that. Still not hitting it. Try again. Step into it. Unary. Tokens, token count 3. We already stepped past everything. Why did we do that? Oh, that's because we need to do next token and not token count. Yeah, another reason to not make it so sloppy, or else you'll start running into bugs like this. Okay, hey, look at that. So now we are returning a unary operator, a unary expression, sorry. Please, data unary, right will be a primary with data t, with 2, and then the operator will be a minus, okay. And so now we need to evaluate that or print that, because I think, yeah, okay, so we don't, in the object evaluation loop, we also don't handle unary, so every step of the way, we're just going to need to throw in more rules. So we can add an expression unary right here. Expression unary, evaluating unary, evaluate unary. So how do we evaluate a unary expression? Depending on what it is, we'll need to determine what the token inside of it is. And I guess you could use either. And we have a lot of flexibility in how we want to choose what to do, because we can just make the bang also set the number to negative. And I don't know, I mean, that'll probably lead to confusion. I'm used to doing it only with a minus, so that's what we'll do. We will do case e data unary operator dot type. It's a token, don't forget. Case token minus token bang. Case, oh, switch. I meant to do switch. Do object O equals null. Return O. And then we have the operator. Let's just say if e data, we need to evaluate the expression inside. So we'll do O equals evaluate expression e data unary operator, no, right, that's it. And I mean, I guess there's nothing stopping us from moving it up here. And then depending on the operator, we can then say if O type equals object number, we can say printf error cannot use bang token on number value. I don't know. What do you want to say? You can say anything. The code is all on GitHub. It's for you to play with. And then we'll do runtime error plus plus. And if it's a minus, then we can do printf or dprint, pdebug, yeah. And then we'll say negating number object d. And then we'll do o.data. No. We'll need to do if O type, yeah. Is a number object, then we'll put it in here, else, and then we'll just do runtime error. And it's a case we haven't handled yet. Printf error unhandled unary case. Error in evaluate unary. Okay. negating number object, and then we'll do O dot O data integer equals O negative O data integer. O data integer. Yeah, the semicolon. Okay. So we're evaluating the expression. Okay. I think that should work. We also need to print it out. So, kind of doing things out of order here. So we handled happens if you want to print it. It's an object. Printing that number. That's all still numbers. Print expression. Going to print unary. Add a new expression for that. We'll just mimic primary or something. Print unary. And then we will print the token and then print expression right. Yeah, and we'll just replace this with unary. Okay, let's see what happens when we do -2. Number object -2. Look at that, people. We got unaries now. Just for numbers. So we can do -2 plus 2. It'll be 0. Dude, look at that. You can now handle negation. Do -2 and it'll be -4. Cool. So we have, just for numbers, we can evaluate plus and minus. I guess we can start adding in multiplication and division. You know, we have the whole pipeline set up, so it'll just take hours and hours to really flesh it out to get the rest of the stuff in here. Of course, you can do that on your own. I'm disconnecting, reconnecting. Oh dear. OBS Studio went down. What the hell? Warning, the stream. What is the stream? Stream's current bit rate is lower than the recommended bit rate. We recommend that you use a stream. Oh dear. Okay, well. Okay. My little camera thing. How long does it... SCZG. How long will it take for you to complete it? I mean, it really depends on what you want to add to it. Like any other problem space, it's infinite with whatever you want to do. How long will it take me? Like what it's been, we've been going for, damn, an hour and a half. Yesterday we streamed for 2 hours to make the parser. Today we added a basic AST and evaluation loop for it. I'd say that I need to add multiplication, division. I want to add strings. I want to add integers, chars. I want to add like assignment operators where you can do like... What I want to be able to do with this is just to make a very basic C-like language that I can then reduce into... So like the plan, right? We have int x equals 0. We have int y equals 1. And then I want to do like x plus y. Then I'll have like, do int z equals 0, and then we'll do like z equals x plus y. So we're going to need to have declarations, and this is where we get into statements. So you have statements which can contain expressions, which then, you know, they can be equality, or I think then you have assignment. And the statements can have like, they can have print statements, at least from what I remember from the way we set it up in crafting interpreters. You can do print statements, you can do expression statements, you can do declarations, which is where you have a type that you declare, like when you int x, this is a declaration. And then this is an assignment where like you've declared z earlier, but then you assign it, and you have assignment like right above equality, and then you have comparison, term, factor, unary, and then you can add in calls for functions. I would like to add functions. And then you have primary. So there's there's more stuff that we're going to add later. We're just getting the basic internal plumbing set up for initial numbered like mathematical operations, but ultimately programming is just like setting up, like declaring pieces of data and then doing stuff with that data and then assigning it to other operators. So we have like several more operators to go. Let's just be very generous with the time that we want to spend on, say, like another 2 hours, and we can have the basic plumbing set up for primary. Like, let's just check off primary. We'll have we already have unaries. We have terms, factors, comparison, equality. Assignment, we're gonna take some time for that. Let's say like assignment takes 2 hours. Let's say like just be really generous with our time and say like calling functions, setting up the function logic, that'll take 4 hours, and statements will take another 2 hours. 2 plus 2 plus 4, that's 8 hours, and then like if we give it another 2 hours, then we'll have all the internal plumbing set up. And this is just to set up a functioning language, so like let's just say 10 hours. And then like we'll need to, I want to demonstrate Pratt parsing, and then also let's say like that takes another 10 hours, I don't know. And then we'll say that we have Pratt parsing, and then I want to break it down into an IR, like intermediate representation, where you take like int x and then you do like push or move into one of the registers, like register 0, the value of like x, which is 0, right? And so that's where you start breaking it down into the registers for the virtual machine, and so that's like another 10 hours. So just to answer your question very roughly, and to give myself a generous amount of time, it'll take me at least like 20, 30 more hours to complete the language. And I guess I should stream every single part. I'm gonna need to, there's steps, there's blanks in my head. Like I know how to do statements, I have an idea of how to do assignment. For the calls, we can probably fumble through it, but I'd like to review the source material from like Crafting Interpreters and some other books. But yeah, 30 hours. And we're already like 4 hours in, but you know, we might go slower, we might go faster. So yeah, that's the idea. And we just got unary for numbers. Do we want to keep going, or should we call it there? We can evaluate the code in the AST. So we're stepping through the AST, like we're not using I guess in a sense this is a virtual machine. If you want to, let's hook up a REPL. Why not? Let's turn it into a REPL. So we'll do, I'll just do while one. We'll wrap this. And I can do like define loop 1, and then we'll just do if loop and if, and the same down here. Just add some preprocessor stuff. Okay, so now we're looping. Let's do like 2 plus 2. Okay, and we're still going. Just type in 2. Okay, so we don't do something. We never clear. That is interesting. Forgetting to do something here. We set next token equal to 0. Oh, we need to do object count. We need to erase all the memory. So object count, we'll need to do expression count equals 0. Token count equals 0. Yeah, just clear out all the memory that we have. Oh god, what did I do? Okay, now we'll do 2 plus 2. 1 plus 2, that's 3. Okay, so now we have a REPL right here where we can type in all this stuff. And hey, that gives us an error because that's a variable which we never return. Okay, I guess we could do that, but then we'll need to, no, I don't want to handle variables yet. Because we typed in like some gibberish, we're going to interpret that as a variable, but then that'll get into declarations and assignment. I guess we can return an error for that, like if the next token, Yeah, we'll just return an error for that, yeah. So, yeah, we're getting to a lot of code, and I've totally lost where we are. Expression. Okay. Yes. Okay, so down here, primary, we can do else processing error plus plus printf unhandled token type, and then we'll just print out a token string, stir token. Where do we print out like the text for our tokens? Toke stir. Okay. Do unhandled. Tokens. Next token plus plus. Okay. Of course that doesn't work. No, I don't want to do plus plus there. Tokens dot type. I think that's it. Oh. Int. Oh. No. Printf requires an argument of type character string. Variadic argument has type int. Why is that? Token type t, feeding in a token type, and we're returning a string. Why is that a problem? Printf unhandled token type. Okay, well that's compiling successfully. Can I just do test? That's compiling successfully. Let's do const char test equals this right here. Okay. Initializing const char differs in the level of indirection from int. Why are we returning an integer? Am I doing something wrong? I'm just going to clean that up. Am I calling this anywhere else? Token string printf keyword found. So this is giving me an error everywhere. So I did something wrong to token string somehow. I'm just going to comment all this out and see what happens. Const char text. What the hell? That's weird. That is so weird. Why is that happening now? Do we ever run this? Like, let's just run it and see what happens. Okay. That is bizarre. Well, anyway, let's just guard against those. So if we have a parsing error, parse error, continue. Then we print out the tokens, and then we process them, and we'll do if processing error, or like expression error, I don't know. Do the same thing. Error in expression evaluation. Okay. Oh, and we'll also need to reset those errors. So processing error equals 0, runtime error equals 0, parse error equals 0, all that stuff. Okay. But I'm still baffled. Const char star token string. Do we have this anywhere else? Well, my treadmill ran out. Keyword found. Okay, let's do like int. Let's see what happens. Int. That is working. Type. Token type. Okay. Oh God. Tokens. Next token. Dot type. I do token t equals this t dot type equals token number, and let's just see what happens. I'll just pass in t dot type. Argument 1. It's not a D. Let's just see what happens. Printf s in format string conflicts with. That is so weird. Are we caching it? Can I just copy and paste this? Like token type equals token number. Oh, oops. Yeah, we're above it. Okay, yeah. We need to move this above, and I was just being a dumbass for the past who knows how long. Let's just move it to the top. Okay. All those print functions, let's just move those to the top. Okay. That's my bad. I was being a dumbass for a little bit. Okay, we uncommented it. That is embarrassing. Okay. Unhandled token type, token string, tokens, next token, dot type. Hey, there we go. Okay, so now let's see what happens when we pass in a variable, because we're not handling it yet. Var int, whatever. Okay. My error unhandled token type. Okay, processing error. And then when we go to print expression, yes, okay. Okay. We won't process them if there's an error, which will make us crash. So now we'll do. Okay, not evaluating. There was an error. Okay, great. We'll do 1 plus 2, something, error, not evaluating. Okay, that's perfect. That's amazing. So yeah, that's why I gave us so much time, because of course there's always going to be instances of me not knowing what the hell I'm doing, and it's just a problem of having the functions out of order. But what we've done so far today, I think I'll wrap it up here. Getting near to 2 hours. It's been a long day. I guess I could, like, just for one, I mean, might as well stretch to 2 hours if we can. So let's do factors. One more thing, we'll do factors. Well, let's turn this into, we can just repeat a lot of the code. And so we'll do a binary expression there, and we'll just turn this to star or slash. And then see if we can evaluate that. We'll do like 2 times 2. Okay, evaluating binary, evaluating primary. Print object, that's because it's going to be null, because I didn't handle all that, but still, I did 2 times 2, and we're not printing that out when we go to print expression. Print expression, that's because I didn't have the token for it. Yeah, so we're going to need to do all that. Slash, star, slash and star. That'll handle the printing for printing the tokens. And now we'll need to add another evaluation to the objects. Subtract objects. Just do all this. We could condense these all into one big function, but why bother? We can do multiply, divide. That will be integers, so we'll also need to handle, once we add floats, we're going to need to add a lot of stuff to this. Well, for my virtual machine, I don't even have floats. I just do integers. So we're just going to keep it integers for now to keep it simple for ourselves. So then we'll add more cases where we'll do slash and star, star, slash, dividing, multiplying, okay. Is that everything? Let's do 2 times 2. Let's do 2 times 3, whatever. 2 times 3, print object. We got a null. Why is that? Slash, star, their number objects. Case, break, case, token slash break, case, token, star. Evaluate. I put it in evaluate term when I should put it into, well, I guess we can do evaluate math. Do I want to split it up? Evaluate term. Is it plus or token? No, let's just make it evaluate math, and then we'll do slash and star. Okay. Then instead of evaluate term, we'll just do evaluate math. Okay. There we go. 2 times 3 is 6. 2 divided by 2 is 1. That's 2 divided by 3. Where did my cursor go? Okay, we hit an infinite loop. Why is that? Is white space. Oh. See. Okay. Yes. Else we'll just skip it. How about that? Or, yeah. I don't know. Let's just do I++ printf, or yeah, it'll be an error. Yeah, let's just make it an error. Error unhandled char, and then we'll print it out. Yeah. Then we'll do parse error plus plus. I think it's parse error. I'll just change parse error to parsing error. To make it consistent with processing error. Okay. And then we will return. Okay. Now let's see. Oh. It's not white space. Oh, that's because, yeah. Okay, so it's not white space, but it's, yeah. We'll add it in there, and then we'll also, let's just add it to 2 places. Why not? Oops. Copy it. Paste it in there. We'll just return. Okay. Okay. Unhandled char underscore. Error in the code, not evaluating. Okay, cool. Then we'll do 1 + 1 1 plus 2 times 3. Yes, 1 plus 6. We'll do 2 times 3 minus 1. And so this will be 5. Otherwise, if it's wrong, it'll be 4. Okay, so that means that's telling us that our precedence, our order of operations is correct. What else? We can do the same for like dividing. 2 divided by 3 will be 0. Yeah, so it'll be -1 if it was like, if we did it like this. Let's wrap it in parentheses, actually. Okay, so we did, okay, I need to reset that string, actually. But we did 2 divided by 3 minus 1. That'll evaluate to 2 divided by 2, but then you see all this gibberish in here. So that's because we never reset that string. So we'll do memset. I guess we can do AST string count equals 0, and that'll probably solve it for us. We just want to refresh, reset all the data between operations. 2 plus 2, 2 divided by 3, yeah. 1 plus 2 divided by 3. I don't know, what will that even equate to? 2 divided by 3 is 0, 1 plus 1, yeah, okay. Cool, so now we have all the basic math operations for real. Plus, minus, subtract, sorry, plus, minus, multiply, divide. We have all that in the language. Of course, there's a lot more to add, like all the different comparisons, and then we'll need to start adding booleans like truthiness. But for now, we just handled simple numbers, and we can figure out how to add the rest of the stuff tomorrow. But from now on, it's mostly just busy work and adding in more functionality to the code. But for today, we constructed the abstract syntax tree with recursive descent, and then using that same tree with that single expression that we generate, we also evaluate it where we need to use objects, which, you know, you can make an object whatever you want. We're just going to keep it simple, and we're just using integers for now. And that's all we can handle. So we did recursive descent to generate an AST, and then we can go through that AST and evaluate it. So that's what we did today, which is pretty cool, not bad. All this code will be uploaded to GitHub. I guess I could split it into days, like day 1 had the parser with the bug in it. Day 2 will have this stuff. I guess I could do that. Yeah, why not? Let's do that right now, and I'll just I'll need to make a folder, day 2, and then we can just drop it in here. Yeah. Okay, so we'll make a copy of it, and then yeah, we don't have assertions or stuff like that. We can do that real quick. Define, assert. We'll have an expression. This is like basically how Casey Muratori does it. If expression, if it's not true, then we dereference 0 and try to set it to 0. Let's just see if that compiles. Yeah. Okay, so now we have an assertion, and that is incredibly useful because if we want to hard stop on anything, we can just do assert 0, which will be false. We'll run it, Windows, and then we will crash right there, right? That is what you want to see. This makes debugging very useful. And how it works is that we just dereference a null pointer. But we set it to 1, so it passes now. You see that? So we'll go back up to where we defined it. An assertion, you just check an expression. You want to check if something is true, and then if it's not true, then you take 0, which is the same as null. We could just write null here instead. You're dereferencing a null pointer, and when you're in debug mode, that'll crash you, and you'll see the exact line that it happened. So very useful tool, assertions, and we can get rid of this to do. So that's just one more thing I added. Day 2, we could undo everything. Why not? Let's just here actually. This is in day 2. We just copy all this to make sure that we don't lose it, and then I'll just undo all this stuff. Discard. Okay. And then we'll see where we wound up. Line test. Oh dear. Okay. Still has all that code that we wrote. That's interesting. Still work? 2 times 3. Yeah, okay. And then if we want to run this, can we just like undo everything that we did? Can I just hold Control Z? Okay. Yeah, it's a bit too much work. I'll figure this out later. I'll download the repository. I'll upload it later. We did good work today. We can evaluate basic mathematical expressions with our programming language. If you want to learn more, you can go to Crafting Interpreters. What I covered was just a piece of Chapter 6 and Chapter 7 where you evaluate them, and then, of course, in these chapters you slap on everything else, but we didn't have enough time for that, and then you get to statements and state, and then control flow and a bunch more stuff. So there's a lot more to do, and by all means take my code or just look at this and learn it on your own. But no, I can't make any guarantees if I'll be doing this tomorrow because I do have a busy week, but I'll try. We'll be on and off developing the language as we go forward. So thanks so much for tuning in, everyone, and I will catch you next time. Bye-bye.